Okay, folks, I can see we just hit 1 minute after the hour. My name is Matt Thomas, and thank you for tuning in to the USGS Landslide Hazards Seminar. This meeting is hosted by the Landslide Hazards Program and co-organized with contributions from Stephen Slaughter and Jamie Kostelnik. For those of you that are new to this meeting, you have the ability to submit questions via the chat window or to use the raise your hand feature in combination with your microphone or video camera. We're going to wait until the end of today's presentation to take questions. So in the meantime, please just do your best to make sure your microphone is muted and your video camera is off when you're not intending to speak. Today, we're joined by Sebastian Uhlmann from Lawrence Berkeley National Laboratory. Sebastian is currently a freelancing scientist based in Potsdam, Germany, and a guest scientist at the Lawrence Berkeley National Lab. He's also a visiting professor at the Mirata Center for Wireless Networks and Applications in India. In 2018, Sebastian obtained a PhD degree in applied geophysics from ETH Zurich in Switzerland, where he focused on monitoring of moisture-driven processes in natural and engineered slopes. From 2012 to 2018, Sebastian worked at the British Geological Survey as a research geophysicist and next to monitoring landslides, also working on the development of near-surface geophysical techniques for resource and groundwater assessment in England, Europe, Southeast Asia, and Africa. In 2018, he joined Lawrence Berkeley National Lab, first initially as a postdoc and then later as a research scientist, and he's worked on various projects related to the impacts of climate change. Last year, he received the AGU Near Surface Geophysics Early Career Achievement Award for novel advances in integrated monitoring and modeling of geophysical, hydrological, and geomechanical processes in the subsurface environment. And I also want to congratulate Sebastian for choosing to join us at 10 o'clock in the evening, Germany time for today's seminar. So Sebastian, I believe that makes you our first international speaker. So thank you very much.
Well, thanks a lot, Matt. And actually, it's 11 p.m. So yeah, it's even an hour later, but that's good. So yeah, thank you very much for the introduction and also for inviting me to give this seminar today. So today, what I would like to do is I would like to give you a little overview of the work that we've been doing in the last couple of years or so here at Berkeley Lab, with regards to characterization monitoring of landslides using geophysics, remote sensing, and wireless sensor networks. And I also want to show you a little bit how we may use that for landslide early warning. And this is basically a project that, of course, has a few people that work on it. So it's mostly myself, but also Sylvain Fiolot, who is the postdoc working on that, Stan Wieland, who's an electrical engineer who did most of the development of the sensor network we're going to show, and Baptiste Davlon, who is also a geophysicist who is working with me on that. Lawrence Berkeley National Lab is a Department of Energy research lab. And so the work that we're doing is not necessarily hazard related. So this project really that frames this work is actually, not focused on landslides, but is more generally focused on stability of earthworks that either form or protect critical infrastructure. So it's all about critical infrastructure. That's the way how we formed or how we developed this project. And critical infrastructure itself are the assets, networks, and systems that provide the essential services that underpin society. And these are, the things that are vital to our safety, prosperity, and well-being. But now a lot of infrastructure is actually at poor condition, and you can see this when you drive around, for instance, at the Bay Area. You can see bridges that are pretty, poorly maintained. You can see some underpasses that are falling apart. So really what we need to do is we need to maintain and manage this infrastructure. But this comes at a cost. And here are just some numbers that, for instance, by 2040, in the US, we will have to spend $12.4 trillion, and worldwide, this will be $94 trillion. So really a lot of money. And now in the future, this infrastructure is increasingly making use of connected technology to really integrate energy systems, buildings, and industry, and basically to adapt and evolve the way we work and live and what we do with this infrastructure. And this is also becoming increasingly important for earthen infrastructure, like, for instance, levees or embankments, and also just the slopes that surround infrastructure, where we see more and more that we have wireless sensor networks, we have digital twins, and other integrated systems and networks that are increasingly being used for landslide mitigation, but also for landslide early warning. So I'm going to show you a little bit of this today. Or I'm hoping to show you a little bit of this today. So in this project, we are trying to develop a novel approach to provide a robust and reliable early warning of slope failure by combining various sensing technologies, which range from low-cost geophysical monitoring, but also environmental sensing, and combine this with hydrologic and geomechanical modeling to basically try and provide a factor of safety of slopes in real time. But also by using these models and feeding them with, for instance, weather forecasts or machine learning-based prediction techniques, we also want to be able to forecast what the factor of safety is doing in the future. And this work really builds on recent advances in various fields, particularly in sensing technologies, where in recent years, geophysical monitoring has seen a number of developments that enable us to perform long-term monitoring of landslides to provide actionable information like volumetric 3D changes on moisture content that we can record before, during, and after landslide movements. And before I go to the work that we've done at Berkeley Lab, I would like to focus a little bit on these developments that are specifically on low-cost, geophysical monitoring, because also, as Matt already said, my background is geophysics, so I know this pretty well, and I thought I'd take this opportunity to also show you a little bit about that.
Hey, Sebastian, before you make the transition to your next slide, I just recommend turning your video camera off.
I will try and do that. Better?
Yep, keep going. Sounds good.
Cool. Yeah. So yeah, this is work that I've done before I actually joined Berkeley Labs, when I was at the British Geological Survey, and there I was working in a group that was developing geoelectrical monitoring, and my task there was basically to develop some techniques that enable long-term geoelectrical monitoring of landslides. And these developments have been done at the Holland Hill Landslide Observatory. This is a landslide observatory that's located in North Yorkshire in England. And it's sitting on a slope that sits within rocks of the Lias group of the Lower Jurassic, where we have Whitby mudstone failing over state sandstone formation. So the Whitby mudstone is a very weak, very clay material that fails then over this kind of sandstone material that's also not really a nice, competent sandstone, but is more like a weak, silty, sandy material. But still, we get these failures in these areas. And actually, geologically, this is pretty typical in England. So in a lot of places where Whitby mudstone is outcropping, that's where you get a lot of landslides. And this map here, we can see the Whitby mudstone here failing basically over the state sandstone formation in this kind of somewhat lighter gray. The landslide itself is reasonably small and has a slope gradient of only 12 degrees, which already shows you how weak this material is. And hence also it shows you how unstable the slope is. So it's a slow-moving landslide with movements that are usually less than a meter per year or so, where translational movements that are happening in this area here are forming these earth lobes. And these translation movements that you have here are actually taking away the support of some secondary slopes in the back, where then you can see some rotational failures. So this shows you that this landslide system is quite complex, where you have translational movement, you have rotational failures, and you have the formation of lobes. Now at this site, we used it as kind of a development site. We have a lot of instrumentation. There are GPS markers that we use to monitor deformation every month or two or so. We have tilt meters that measure deformation, but we have also piezometers, soil moisture sensors, and these type of sensors that are measuring basically the hydrology of the system. And then we have outlined in red here an electrical resistivity tomography system that was measuring the resistivity of the ground every other day. And this is something that we can then use to actually track moisture movements in 3D, and I will show this in a second. But before that, I thought I'd show you how we characterize the landslide using a different geophysical technique, in this case, P and S wave seismic refraction measurements that provide us with the P and S wave velocities or P and S wave velocity variations in the subsurface. Now, for those of you who are not geophysicists, the way you do these kind of surveys is you take basically a sledgehammer and you hit a metal plate, or in this case, a metal prism. And by doing so, you're exciting some waves that are traveling through the ground. And every time you get a contrast in seismic velocities, and the right angles, you get a refracted wave that's basically traveling along this interface. And while traveling along this interface is kind of exciting additional waves that you then measure using geophones. In this case, these geophones are shown here, and we use 3-component geophones because that enabled us to not only look at the P wave, so the pressure wave that's going through the ground, but also the shear wave. And having both is actually pretty nice because the P wave is sensitive to, for instance, variations in fluid content in the ground, which the S wave is not. So by having the two, you can also make some assessment of where you don't have any moisture on the ground. And we were doing these surveys to try and get a good understanding on where the interface between the Whitby mudstone and the state sandstone formation is. Now, if you look at the results that are shown here, you can actually see that we don't see this interface. We were expecting the interface to be somewhere around here, but as you see, there's nothing that you see in these images that indicate any interface of two geological units. What we do see, though, is some high velocity anomalies, especially down here and up there, which relate to the regional groundwater table that you can see here and the purged groundwater table that you can see up here. Now, if you look at the S-wave velocities, really the only thing you can see is kind of a weathering horizon. So the deeper you go, the higher the velocities. So the shallower material is just much more weathered than the other material. But as I said, we had both. We had P and S wave velocities in this case. And what we can do with that is we can calculate the ratio between them. In this case, we calculate the Poisson's ratio because that's an elastic property that's very well defined. And to keep it very simple, if the Poisson's ratio is small, so in this case, if it's red, this means that the ground is dry. And if the Poisson's ratio is high, so if it goes towards 0.5, that means that the ground is fully saturated. And now suddenly we could really see this interface between the Whitby mudstone, which is the saturated blue material that we can see here. And then underneath that, we saw this kind of drier material, which is the state sandstone formation, which is a formation that is much better drained and hence has much less moisture, especially in the top part of it. And if we look at this in 3D, we can see that we could really nicely track this interface across space, and we could basically have a good idea on what the lithology at the site looks like. And then what we did is we also did resistivity tomography. And the reason for that is that the resistivity of the ground is actually a very nice indicator of first the lithology, but also the water content and how the water content may change over time, and also the temperature of the ground. So especially the water content is something that, for landslide studies is super interesting, because if you can track how water is moving in 3D through a landslide, that tells you a lot on what's going on. And the way we do these measurements is we basically have electrodes in the ground, and we, in this case, we have 196 electrodes distributed across this site. And then we do measurements between 4 of them every time, and we just swap them so that we can try and sample the ground as densely as possible, as kind of is indicated in this schematic here, where depending on how you choose these 4 electrodes, you sample the ground at different locations. And then you need to do an inversion to basically recover what the resistivity distribution in 3D looks like. Now, as I said, the resistivity depends on the lithology, and we can see this very nicely here, where we can see very nicely where we have the Whitby mudstone formation, because that's where we have basically these low resistivities, and that's mainly because the Whitby mudstone formation is very high on clay content, or has a lot of clay, has a lot of water, and so the resistivity is very low. And underneath that, we have the state sandstone formation, which has less clay, less water, and hence has a higher resistivity. Now, the nice thing about these resistivity measurements are that if we repeat them over time, we can assume that the lithology is not going to change, but that the only thing that's going to change is the water content and the temperature. Now, the temperature, we actually measured at the site, and so we know, how the temperature varies across space, well, how it varies laterally, but also how it varies with depth. So we can correct for that. Now, the other thing that we can do is we can take samples from the site and analyze them with regards to their moisture content. So we did this. We took samples from the Whitby mudstone, the state sandstone formation. We took them to the lab and measured how the resistivity is changing at different moisture contents. And having this basically allows us to create a model that we can then use to translate the resistivity that we measure into a moisture content. And now we can see this here, and we can see again that we have very high moisture content in the Whitby mudstone formation. We have lower moisture content in the state sandstone formation, but we can also see a lot of detail, where, for instance, here we can see an area of slightly elevated moisture content, which is basically an area where every time we went to the field, we can see, or we could see some water coming out of just the head of the lobe. And so we saw, a little spring that was there. So in this video that I'm going to show now, I'm basically going to show a time series across the monitoring period that I analyzed a couple of years ago. So first we see again, how the Whitby mudstone formation in blue here is kind of riding over the state sensor formation in red. We can see how the lobes are forming. And now in the following, what I'm going to show is just the changes in moisture content that we calculated, just to give you, an idea of how we can track moisture movements in 3D. And basically we start in winter, where we could see high moisture content here. We go then further into a summer month, where we can now see how, the water is basically draining in this lower part of the slope. And basically this water that is draining here in summer is what accumulates in winter up here. And we can see again now in summer these patterns that will appear here. So that's something that is happening every year. So now we're getting into the year of 2012, which is when this slope reactivated, this landslide. And this was a year where we had exceptional amount of rainfall. So already the summer is now much wetter than the year before. But now if you look at winter, it was really, really wet. And that's where we had some rotational failures in the back, but we also had a massive translational movement of these lobes that formed there. So unfortunately it went back, but here I have just a few of those plots to show you again, the drainage. So we have this water that accumulates in winter here and then drains in the summer here. So that's something that we can see every year. But what was more interesting was actually what we saw during December 2012 when we had this reactivation, because what we were expecting to see was a lot of movement on this side. So one of the lobes, because when the landslide failed before in 2009, that's when we saw, or that's where we saw most of the movement. Now in 2012, actually, this lobe didn't move at all. It basically remained completely stable. And what we found is that, we had this interesting pattern of moisture movement, which indicates to us that we had some preferential flow where we had some relatively big fractures in the surface that allowed water to infiltrate relatively deep into the ground. And then underneath this lobe here, you have some aeolian sands. So they were really nice as preferential flow pathways, and basically took the water away from the slip surface, reduced the pore pressures at the slip surface, and actually stabilized the slope. So this is something we didn't have on the other side, on the eastern lobe, where we see this accumulation of moisture on the top here. And this is basically the site where we got about 3 meters of movement in just less than 2 months. So there was a lot of movement on this side, which was basically triggered by this additional load of moisture that we managed, or that we imaged up there. So this just shows you that geophysics can really reveal some processes that control landslide movements, and can do this in 3D or even 4D in this case. So then we were also looking how we could use this potentially as for early warning purposes, let's say. And for this, I extracted the moisture content at these, the top part of this eastern lobe, and what we can see is basically some seasonal effects. We can see that we have low moisture content in summer, we have high moisture content in winter, and in general, over the period that we analyzed, the moisture content basically increased over time. This also agrees with the water levels that we measured, which also shows some sort of seasonal behavior, but also clearly show this rise over the couple of years or few years that we monitored this. On the bottom here, what we see is a displacement record. So first we see that we had a little bit of creep, there was not much movement, but then as soon as we hit the winter of 2012, 2013, we see really that the slope started to accelerate and had a lot of movement. Now, if we relate this to the measured moisture content, we can actually derive a threshold. In this case, we found that if we have more than 48% moisture content in this part of the lobe, so just above the eastern lobe, that's where we have to expect movements. And now if I would extend this plot into the future, and actually we have all the data because the system is still monitoring, every time we exceed 48% is actually really where we see movement. So this threshold proved valid in the last few years. So this was just to show you, what you can do with geophysical monitoring, let's say. The problem that you have with that is that it's very site-specific. So that's something that you can do on a place where you know you have a problem, right? Where the problem is severe, and you want to understand it better. And that's actually also how the British Geological Survey is using these techniques. They're working together quite a lot with, for instance, Network Rail, which is the railway provider in the UK, which often asks them to install these kind of systems at areas where they really have a big problem with slope instabilities, but they really don't know what's triggering the slope instability, for instance. So they're using this as a measure to really image what's going on the ground, to then design some mitigation measures. But now what we want to do is we wanted to bring this a little bit further and upscale it. And that, of course, is not possible by just using geophysics alone. You also need to combine this then with some environmental monitoring, some remote sensing, and then, as I already mentioned, combine it with hydrological and geomechanical modeling to get to basically a prediction of factor of safety for an entire site. And that's something that we try to do at Berkeley Lab, because Berkeley Lab is located in Berkeley in the San Francisco Bay Area, where the Berkeley Hills and the Oakland Hills really have a history of landslides. There are many deep-seated landslides, which are basically shown in this map here. Most of them are dormant, but there are also quite a few active landslides. But next to these deep-seated landslides, you also have a lot of shallow landslides. And that's something that we were mostly interested in. And what we focused on is basically my office, so Lawrence Berkeley National Lab, or the campus of Lawrence Berkeley National Lab, because as you can see in this other map here on the right, also there we have a lot of landslides. So you have a lot of paleo landslides. So for instance, out here you have an old landslide. You have some here. Most of them actually happened during the development of this site, where they did a lot of excavations, changed the slopes quite significantly, and then you get a lot of landslides. But also more recently, you get quite a few landslides. So one of the active ones that is still creeping is Chicken Creek landslide that you have here. You have one that's called LS40, so likely being called LS40 because landslide number 40, which is affecting a bridge here. So I will focus on this in a little bit. But basically what you can see is there are a lot of landslide at this site, but also in terms of landslide risk, we have a very high landslide risk because we also have a lot of elements at risk, right? So we have unique scientific facilities in this area, and not only here, also down slope, just in the UC Berkeley campus. So really, we use this as our field laboratory and try to develop some of these techniques of combining hydrological and geomechanical modeling with remote sensing and so on at this site. So first, what we try to do here is really we first aim to assess the landslide hazard through some geostatistical and hydrogeomechanical modeling, which we did here using the Python package landlab. Landlab basically takes a digital elevation model of the area, so DM, which we had a very good one because there's high resolution LiDAR data in the area, and then you take distributions of various input parameters to basically calculate a landslide probability. And before we ran this model with the basically distributions that we knew that we had to expect, we ran it just in sensitivity analysis. And that's something that's shown down here, where we basically estimated how much influence each variable has on the outcome of the model. And what we found is that really the most important variable is the slope angle, followed by the soil thickness and the soil cohesion. And less important are soil density, the friction angle, the transmissivity, and the water recharge. So basically, water recharge is just basically defining your precipitation pattern over the year. But so basically, we had to know the slope angle and the soil thickness and the soil cohesion. Now, the slope angle, as I said, is something that we can get pretty easily because we have high-resolution LiDAR data, so we didn't worry too much about that. But we had to find ways of estimating the soil thickness and the cohesion across the site. So the soil thickness, we estimated basically combining borehole information that we had from the site, and then some geophysical measurements, and in this case, ambient seismic noise measurements. And we did this because the boreholes that are shown in blue here are in locations that are not necessarily particularly useful to make an assessment of what the soil thickness of the slopes in this area are, because most of these boreholes are actually at points where they needed to build a new building, or it's mostly that actually. They're mostly at sites where they had to build new buildings, so they're just trying to estimate what the conditions are in already developed areas. So there were very little boreholes that were actually telling us what the soil thickness is. And so we added these ambient seismic noise measurements, which basically just means you take a 3-component geophone, you put it out in the field, you record for half an hour or an hour or so, and then you calculate the spectral ratio of the horizontal to vertical component of the signals that you measure. And what you get from that is basically just the resonance frequency of the ground. And you can see this in these plots down here. And this resonance frequency gives you an indication of what the soil thickness is, because usually the resonance frequency just depends on the soil thickness. And the higher the frequency, the thinner the soil cover, and the lower the frequency, the thicker the soil cover. Now, to really translate these peaks in frequency into a soil thickness, you need to know the shear velocity of the ground. And we were lucky because there are quite a number of shear velocity measurements across this site. So we had a very good idea on what the expected shear velocities are. So we could actually translate these peaks into a soil thickness, add this to the borehole measurements, and then interpolate it across the site to get a good understanding of what the soil thickness is across the site. And then the second parameter that we had to know is the total cohesion, which is the sum of the soil cohesion and the root cohesion. So the soil cohesion is something that we could get from all these geotechnical drillings that we had across the site, but what we needed to better understand is the root cohesion. And basically what we did is we used some planet data, so some high resolution aerial remote or optical remote sensing data, has a resolution of about 3 meters in this area. And we took this at various times across the year, and then trained a machine learning model to predict which vegetation type we have across the site. And we made it awesome. We made it ourselves somewhat simple in that we only distinguished between what is high or what's tall vegetation, what is low vegetation, and where do we really have vegetation. So where do we only have either bare soil or grass? And then by employing a simple root density function, we can actually calculate what the root cohesion is with depth, depending on each vegetation type. So that's then bringing us the total cohesion that we need for the model. And then the other parameters, which the model is not that sensitive anyways, like the friction angle or the soil density, is just other parameters that we took from the geotechnical drilling and from soil testing that had been performed at site. And then we ran this model, and basically the outcome is shown here. So what we get from it is just a probability of failure that's coming from a Monte Carlo simulation of basically an infinite slope model that is implemented, as I said, in LandLab. And then we can see areas that have high landslide probability, particularly in the eastern part of the site, which is also where my office was. I was actually sitting here, so just below, this very high landslide probability, but also actually sitting on one of the old paleo landslides. Then we have high landslide probability in this area, and we also have high landslide probability in this area. So now we know, where we have kind of high landslide probability across the site. So that's something that we later on use to then also decide where we put our sensor network. Now, the other thing that I already mentioned is that to calculate these landslide probability, we also included the vegetation distribution. That's actually pretty neat, because it also means that if the vegetation changes, we could recalculate what the landslide probability is. And in this case, where you have active vegetation management, but also wildfires, that's actually very interesting. And we had one of these cases. In this case, one of the areas had eucalyptus trees that were pretty tall and were actually pretty close to a power line. And so PG&E decided that they had to go because they were wildfire hazard. And so we were actually able to recalculate, or to calculate what the landslide probability was before and after this removal of the eucalyptus trees. And we can see the change here. And what we found is that in areas where we had thick soil, so where the soil was thicker than roughly 3 meters, we saw hardly any change. So here, that's shown here, where we see, basically not much change at all. And then for the other area, where the soil was relatively thin, the removal of the eucalyptus trees actually really increased the landslide probability. And we talked with site management, and they're actually fully aware of that, and they're now they're kind of implementing a vegetation plan, but actually putting some native oak trees, and they're putting some small shrubs and bushes here to basically help the vegetation, or to use the vegetation to stabilize the slope. Now I would like to go to the next slide, but yeah, there you go. It's just a bit slow. So the other thing that we did is we looked at another site. As I said, we were kind of interested, or it's nice to get the landslide probability distribution across the site, but we're also interested in better understanding landslide dynamics, and in particular the landslide dynamics of a landslide, this landslide 40 that's out here, which is affecting this bridge. And so at this site we did various things, a range of geophysical techniques, and I will talk about two of them. So first, I'm going to show you some of the characterization that we did, and a relatively small scale, but basically we measured again the P and S wave velocities. So we have P wave velocities. This is actually S wave velocities, even though it says P wave velocities, but it's S wave velocities. And we can see how they vary across the site, which basically shows that we just have a pretty slow velocity material that's overlying more higher velocity ground, so pretty weak material on top of more competent rock. And basically what we have too here is basically the interface between the Moraga formation and the Orinda formation, and in this case the Moraga formation is somewhat more permeable than the Orinda formation. And if we look across the site, almost at every place where we are at this interface between these two formations, that's also where we see some landslides, which is probably just because we get water that's coming from the Moraga formation in the Orinda formation that just cannot go anywhere, and we get rise and pore pressures that's then driving some deformation. So as I said, we have this bridge here, which is actually being heavily affected by this creeping landslide. So the landslide itself is moving by about 10 millimeters a year, so not a lot, but it's actually having a big effect on this bridge. And at Berkeley Lab we use advanced monitoring instrumentation. So one of them is a ruler that is just measuring how much this bridge is deforming. So we're just looking at one of the pillars of the bridge here, and basically you have this ruler that's measuring how much it's deforming. The only downside of such instrumentation is that every now and again it falls off, and then it has to be re-glued. So really, it's actually of not much use. So, but anyways, I mean, they're monitoring the bridge, and actually right now completely rebuilding the bridge. So they're having good bit of construction there at the moment. But basically what we did here is we installed a range of instrumentation along a short transect that's shown here. So we have again some resistivity tomography, but what I want to focus on first is actually some ambient seismic noise measurements that we did in October of 2021. And at that time, we got about 150 millimeters of rain within 24 hours. So pretty significant rainfall event that actually caused some of the deformation. And so what we see here is basically the results of these ambient seismic noise measurements. So what you do there is you just record the seismic wave field as it's happening around you. So it will be the noise from cars, it will be the noise of the trees moving around in the wind, it will be the noise of the waves in the bay. So everything that is kind of going on around you is what we're measuring here. And then what we do is we correlate the signal of each station to itself. So we correlate basically what's happening 48 hours before to what we are recording right now. And then what you would expect if nothing is changing in the ground is that you get a very high correlation coefficient, because basically your signals don't change if nothing in the ground changes, because the noise you can assume over time is pretty constant. But that's not the case, and that has been shown in other papers too, that when you get landslides, you actually can get some responses in the ground that sometimes happen hours before actual movement. And that's also what we saw here. So first, before the rain started, we get this high correlation coefficient, which is shown in red colors here. But then as soon as the rain starts, we get these lower correlation coefficients. And in particular, at the beginning, we get them at the higher frequencies, which means that especially in the shallow subsurface, things are changing. And then later on, we see that we lose the signal throughout almost all the frequencies. And we basically, so our correlation coefficient almost goes to zero. And this shows us that we get, a disturbed ground, not only at the surface, but also at deeper layers. And here in this case, this happens around here. And then 6 hours later is when we see some significant movement throughout the soil column. So this plot here shows you displacement from basically the surface down to 1.8 meters depth. And I will talk a little bit more about these deformation probes in one of the following slides because they're pretty neat. But this is basically for the bottom sensor. Then we had a sensor that was further to the top, and we can see a similar thing again, right? So we see the loss in the signal throughout the frequency range, and then about 3 hours later in this case is where things start moving. And in this case, as you can see from these plots, this is really small movement. There's only like, up to 10 millimeters of movement, so that's not a lot, but we see significant movement that we can resolve with these probes pretty nicely. And the interesting thing here too is that, we get first movement at the bottom, then at the top. So basically what this means is, we get some movement down here that's releasing some stresses, and then we get some movements up there. We also, as I said, we had an electrical resistivity tomography line installed at the site, and we were basically using that to better understand how these winter storms cause variations in groundwater conditions and how these changes then the slope stability. So we monitored the electrical resistivity of the ground using electrical resistivity tomography, and the tomograms are shown again here, where we can see the conductive paleo landslide deposits, so probably highly saturated. Above here we have the Moraga formation, and below here we have the Rinda formation. Now, usually what we would expect when it's raining is that the resistivity would decrease, usually because just we get an increase in saturation. In this case, we actually saw an increase in resistivity, which is mostly because we have in summer really high conductivity pore water that then during the fall season and winter, where you have a lot of rain, is washed out and replaced by more resistive rainwater that's coming into the system. So in this case, we can track the groundwater just by looking at these negative changes. And when we do that, is we can actually really nicely extract where the groundwater table is, and we can put this into simple, infinite slope models, and we can calculate how this changes the factor of safety of these landslides. In this case, or of these slopes. And so in this case, what we found is that, beginning before the storms, we had a factor of safety of about 1.42. And then after the storms, when the groundwater table rose a little bit, by not much, just by half a meter or so in places, we see that the factor of safety goes down to 1.38. We also had a student working on developing some automation of this. So we used unsupervised clustering to extract the groundwater table, and we could use this then to really get these updated factor of safety in almost real time. So that's something that you can do with these kind of monitoring techniques. So from monitoring, again, we can understand how the soil moisture conditions indeed play a critical role in landslide processes at Berkeley Lab. And as I already mentioned, this is really great because you can get a very good understanding of how things are behaving. But as I also shown, we only focused on this site. It doesn't tell us anything about what's happening anywhere in other areas of the site. So what we decided to do is we decided to install a wireless sensor network, and you can see the sensor network that we installed here. So it's quite dense. We have a lot of sensors. We have 18 locations where we measure soil moisture and suction at 3 different depths, at 10, 50, and 30 centimeters depth. And then in addition, we have some deformation probes that I will explain on the next slide. And we installed them at 60 different locations to get a good estimation of where things are moving and where things are stable. So these probes, they're actually pretty neat. We basically built them based on some developments at Berkeley Lab that were focused on temperature measurement. So we do quite a lot of research also in the Arctic and in mountainous environments where it's very interesting to see what soil temperatures are, but also what, for instance, snow temperatures are. Because if you monitor them over time, you can estimate soil hydraulic properties, but you can also estimate snow properties. Now, what we did in this project is we also added 3-component accelerometers to this probe. And basically what we have is now an alternating array of temperature sensors, and then basically a 3-component accelerometer. And we have this every 5 centimeters. So every 5 centimeters, we have a temperature probe, then an accelerometer than a temperature probe. So basically, we have every 10 centimeters then an accelerometer. And these are all built on these flexible PCBs that are shown in the middle here. And basically, they allow you to really bend the probe without it breaking. And we get pretty nice deformation data out of that. So far we have them, or we built them modular so that we can have them, any length between, in our case, 20 centimeters and 1.8 meter length. And basically we limit it to 1.8 meter length because the way we install them is just we take a long drill bit, we drill a hole in the soil and just slide them in. This makes installation super easy and super quick, but if we would make them longer, it would just make installation much more difficult. And also, as at many other sites, at Berkeley Lab, you need a penetration permit to do a lot of things. So the bigger you make your excavation or penetration, the more paperwork you have to file. So this was also one way of making it relatively easy for us to install these. We didn't only install them in the field, we also test them in a lab. And what we found is that we have an accuracy of about 2 millimeters per meter of probe. But also we have sub-millimeter sensitivity, and we can see this in this plot in the middle here, where I just very slightly moved the probe and looked at the change in basically the set location. And in this case, this is really little, so you have less than a millimeter movement. But even though you may not be able to really resolve how much is moving, you really get every time when the probe is actually moving. So you have sub-millimeter sensitivity in this case. And then the system itself has a logger, of course, which is also very low powered. So the entire system, including logger, operates off 2 AA batteries. And if we don't turn on data transmission, the system should be running, at 5-minute sampling interval for about 3 years on these 2 AA batteries. Now, if we enable LoRa communication that we have on it, so long range communication, this battery life decreases. But because we came up with some good data compression techniques, and also we are not using LoRaWAN, but we are using our own communication protocol, still we have a battery life of about 1.5 years of 2A batteries, even though they're transmitting. So we deployed quite a number of them at Berkeley Lab, but we also deployed them in the Arctic, because also it's a good example, and also it's a good test case, because in the Arctic, what you would expect is where you have frozen ground, that's where nothing should move, because it's it's frozen into place. And where you have unfrozen ground, that's where it should move. And these are just some examples of this here, where we can see really that in the frozen ground, nothing moves. But as soon as we're on the unfrozen ground, we get movements of about 10 millimeters in a period of about 5 days in this case. So really these probes work very nicely to get your soil deformation in the very shallow subsurface. So the data from these deformation probes and the soil moisture sensors then transmitted via LoRa to a base station, which receives and decodes the data and then passes it to an influx database, which is an open source database that has been specifically designed to work with time series data, so really, really handy for us. And we have this in the field, and it's operational now since February last year. And so we have quite a lot of data, also because before we actually installed all the LoRa connectivity, some probes were already there since October 2019. So quite a lot of data that we have, and all of this data is now being fed into Grafana, which is an open source browser application that we're using to visualize all the data. But unfortunately, this needs a user account, so it's not a public service right now. But we're also working on a public data portal so that everyone can get access to the data that we're acquiring. And just to reiterate that really changes in soil moisture and pore pressure really make a difference at the site. So here we see some example of the data that we acquired. So on the top we see just some data from the suction sensor. So we see water potential, which shows the response after one rainfall event that we had in April 2022, so last year, where we had a rise in pore pressure that then caused a displacement, in this case, of just 1 centimeter. So clearly, a little bit of change in the hydrology in this case causes quite a bit of movement of at least the very shallow subsurface. And so just because you may have heard that we had pretty bad storms in the Bay Area, or almost all of Western United States in the last few weeks and months, here's some of the data that we acquired during this period. So we're starting in September 2022. And basically what we are seeing here is the interpolated moisture content, and the moisture sensors are shown here in these diamonds. And then we can also see the recorded deformation that is shown in these dots here, where the more red they become, the more movement they've seen. And basically, yeah, we start in September, so there's not much movement. There's not much moisture content in the ground. Most of it is actually less than 5%. We get into October, still no change. We see a little bit of creep here, which is just some of the creep, in the eastern part of the area, where we just have a constant bit of creep. That's also the old landslide sites. Then if we go to November, that's where we already got a few rains. We see that the moisture content is slightly increasing, but still there's not much. There's also not much movement. Now if we go into December, that's already when we had quite a number of rainfall events, and we see that the moisture content is rising. We see now some more deformation, especially in this area. And now if we go to January, we really see how the site is completely saturated. Everything is basically fully saturated. The variation that we see here is just changes in the porosity of the soil, which basically doesn't allow for higher moisture content. But we can also see very high movement rates up to 7 centimeters. And give it a bit of time. Now we had a few weeks without much rain. Actually, moisture contents decreased again, but things had moved by then already. And we see again that in some areas we see higher movement rates on the top of the slope, and then lower movement rates at the bottom. And we can also see this in for instance, the western part of the site. And then if we look at the Grafana interface, that's what it looks like. And we see, here we just plot the pore pressure, and basically red is bad. And almost all of the site is still in bad conditions, where we have very high pore pressure across the site. And then here we also see the moisture content recorded, and especially during January, we see how every rainfall event really leads to a rise in pore pressure, which basically is just the head that the rain brings that just gives rise to the moisture content again. And just to kind of finish up, I want to show you a little bit of the work that we're doing with regards to machine learning and prediction. So what we're trying to do here is basically we try to use machine learning to predict what's going to happen in the future, to basically make this sensor network adaptive. So to basically save data and basically record as in small sampling intervals when nothing is happening, but then increase the sampling interval automatically when we expect changes to happen. And then the other thing, of course, is trying to predict further into the future to provide some more early warning. And that's what we did here. So we tested two approaches. First, predicting the next 1 hour based on the previous 24 hours. And second, we predict the next 12 hours based on the prior 14 days of data. And here in these plots, basically blue is the input data, green is the true data, and yellow is the prediction. And what we use for it is a 1-year time series of actual and antecedent rainfall. We use temperature, relative humidity, and barometric pressure just as the kind of parameters that we use to train the model. And then we can see that actually the results are pretty good for predicting just 1 hour. So we're usually pretty close to the actual values. So we have very high prediction accuracy. But then if we look at longer term forecasts, in this case 12 hours, it's good if we have just gradational changes, as for instance here. So we see that, yeah, prediction is pretty good, but it's pretty poor if we have sudden events. So where we have sudden increases in moisture content, it really doesn't work. And that's mostly because here we just trained on 1 year of data, and 1 year of data where we only had 3 storm events. So really there was not much data to train, especially for these kind of sudden events. So we think here that we have sufficient accuracy for adaptive sensing strategies, but really we need more data to predict more accurately in the future. And that's also what recent review papers all show, that if you want to do long-term prediction, usually it doesn't work that well, and your accuracy isn't particularly good. And that's probably because you need quite long time series to actually cover these extreme events that then cause especially landslides. And just before I finish up, I want to show you also some of the data from the Arctic, just because, in Berkeley, we saw 7 centimeters of movements and not a lot. Here we actually see, well, in this case, it's only shown until 5 centimeters of movement, but we can see from these plots here that we actually see up to 30 or 40 centimeters of movement. So here really we have a lot of movement in the Arctic. And what I thought is very nice to show you here is also why having co-located temperature and deformation measurements make a lot of sense. Because here, of course, we are in an area where we have permafrost, where we have unfrozen ground. And as I already said earlier, what we would expect is that nothing's changing in the frozen ground, but that we see mostly movements in the unfrozen ground. But it's something that you would expect, but it's very difficult to show, except if you have these probes, because what we see now is basically that we have most of the movement occurring exactly at this interface between the unfrozen and frozen ground, which is shown here just by the change in the angle of the accelerometer. So that's the gradient of the measured accelerometer rating, and it shows really nicely how basically this the slip surface follows very nicely this interface between the frozen and the unfrozen ground. And this brings me to the end. So what I was hoping to show here is basically an approach that we're working on that tries to integrate various sensing techniques. So we're integrating remote sensing, geophysical and environmental modeling with hydrological and geomechanical modeling to get to a factor of safety assessment. Of course, this still needs development. I mean, so far what I've shown is mostly, a characterization of the site using a combined hydrogeomechanical model and some very simple models where we integrate geophysics with environmental monitoring to, for instance, track the groundwater table and see how this changed the factor of safety. But really where we want to go to is take all of this data, take the 3D distribution of the different parameters and get really a nice 3D representation of the factor of safety. And yeah, what we still work on in terms of the sensor network and so on is a public data portal so that everybody can access to it. And we're also still working on some machine learning algorithms that maybe could avoid doing these kind of framework where you first do all the measurements, then run the models, where maybe we could just run the models beforehand on a set of scenarios and then use this to train a machine learning model to actually then assess what our field data means basically in real time without having the need to run these models. And one thing that's nice, all this work first was just a research project, but actually now is being taken up by the site management of Berkeley Lab, which is taking our data and is actually, is asking us what to do and how to try and mitigate the landslide hazard, and asking us, where do we have very high hazard, where's the hazard smaller, what was now the impact of the storms that we saw, and so on. So really we're starting to integrate the data that we're gathering into the site response at this site. And yeah, that's all I want to talk about. So thank you very much for your attention. And if you have any questions, I'd be very happy to answer them. And if not now, just send me an email and I also get back to you.